Welcome, I am Derek King, your tutor. In this video today, we'll be looking at a brief summary of circular motion. The motion of a particle in a circular path is called circular motion. The motion of a particle in a circular path with uniform velocity is known as uniform circular motion. Let us define some terms which we'll use throughout this lesson. The angular velocity, omega, is the angle covered by the radius vector in 1 second. The period of revolution, t, is the time taken to complete one revolution. The frequency of revolution, f, is the number of revolutions made in 1 second. Consider a particle moving along a circular path of radius r. Initially, the particle is at the point A. After t seconds, the particle reaches the point B. Let theta be the angle swept by the radius vector in t seconds. If theta is very small, the distance AB will be considered as a straight line. Let v be the linear velocity of the particle, and then the linear velocity v is given by the displacement per unit time s on t. In triangle OAB, sin theta equals opposite over hypotenuse s on r. If theta is very small, then sin theta is approximately equal to theta in radians. Thus, s equals r theta. The linear velocity v becomes v equals omega r. Consider the diagram again. Initially, the velocity component in the AO direction is 0. After t seconds, the velocity component in the BC direction is u sin theta. Since theta is very small, the direction BC is close to AO. Thus, the change in velocity towards the center of the circle, which is the initial velocity minus the final velocity, is given by u sin theta minus theta equals u sin theta. The acceleration in 1 second given by the time rate of change of velocity equals v sin theta on theta, which can be simplified to give a equals v omega. And since v equals r omega, a can be written as omega squared r, which equals v squared on r. Consider a particle tied to a string and whirled round in a vertical circle. At the point A, the centripetal force Fc is provided by the sum of the weight and the tension T1. At the point B, the tension T2 equals the centripetal force mv squared on r. At C, the tension T3 minus the weight provides the centripetal force. So the string is most likely to cut at the point C, as the tension T3 is greater than T2, which is greater than T1.